Hi, welcome to Exponential and Logarithmic Equations. My name is Tuesday J. Johnson, and I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This is for Math 1508. It's a pre-calculus class at UTEP. Chapter 3, Exponential and Logarithmic Functions. Comes to us from Larson's Pre-Calculus, 10th edition, section 3.4, Exponential and Logarithmic Equations. So here's some strategies, and these are not steps, they're different strategies. Strategies for solving exponential and logarithmic equations. First, we can rewrite the original equation in a form that allows for the one-to-one properties of exponential and logarithmic functions, and we'll see some examples. I'll talk you through those as we get to them. These two are essentially the same thing, but they're in reverse. Rewrite an exponential equation in logarithmic form and apply the inverse property of logarithmic functions. Okay. We could rewrite a logarithmic equation in exponential form and apply the inverse property of exponential functions. So if we are looking at a logarithm and the variable is inside the log in the argument of the log, we could rewrite it as an exponential to get it out. If the variable is in an exponent of an exponential, we'll rewrite it as a logarithm in order to isolate it. That's our general strategies. Now, if we start with something simple, like 4 to the x equals 16, don't let it overwhelm you. Keep in mind, 16 is the same as 4 squared, and the one-to-one property of exponential says, if two things with the same base are equal, then their exponents must be equal. So if 4 to the x equals 4 squared, it must be that x equals 2. If I have 1/4 to the x equals 64, I could rewrite 1/4 as 4 to the negative 1. I can write 64 as 4 cubed. So I'll have 4 to the negative 1 to the x, power raised to a power, I multiply. So 4 to the negative x equals 4 cubed. My property says that negative x equals 3, but we always want to solve for the variable, not a negative variable. Let's be positive, people. So I'm going to multiply both sides by a negative 1 to get x equals negative 3. And you can always check it in a calculator. Enter it just like this, in parentheses, 1/4, close parentheses, to the power of negative 3. Pretty sure that's going to be 64 for you. If we have the natural log of x minus the natural log of 5 equals 0, we can add natural log of 5 to both sides, and we find that the one-to-one property of logarithm says, if the log of base a equals log base a of something else, log base a of x equals log base a of 5, say. In this case, our base is e, obviously, natural log. Natural log of x equals natural log of 5, it must be that x equals 5. The one-to-one property of logarithms requires same base on the logs, just like the one-to-one property of exponentials requires the same base on the exponential expression. And we could even make it look harder. E to the 2x equals e to the x squared minus 8. But the one-to-one property says, hey, exponents have to be equal. 2x equals x squared minus 8. Anytime I'm trying to solve an equation that involves a quadratic, I'm going to set it equal to 0, use the zero factor property. So I'm going to subtract 2x from both sides. 0 equals x squared minus 2x minus 8. Now I want two things that multiply to be 8, that are opposite in sign, and they're different by 2. So I'm going to have x minus 4 times x plus 2 equals 0. Factors, x minus 4 and x plus 2, turn into zeros of x equals 4 and x equals negative 2. And if you check these values in the original, they're going to work out for you. If 2 to the x minus 3 equals 32, I'm a mathematician. I happen to know that 32 is a power of 2. So I would rewrite 32 as 2 to the 5th power. 2 to the x minus 3 equals 2 to the 5th, that must be that x minus 3 equals 5. If x minus 3 equals 5, add 3 to both sides, and I get x equals 8. But we don't have to do it like that. There's another way we could solve this problem. We could solve this problem by rewriting x minus 3 is the power to which I raised 2 in order to get 32. I can add 3 to both sides. Log base 2 of 32 plus 3. Written off there over to the side. Yeah, ugly but effective. And you can evaluate this on your calculator. if you're allowed the use of a calculator. If you're not allowed the use of a calculator, it's handy to know things like 32 is 2 to the 5th power. But this method of rewriting in log form will always work if you don't recognize the base that this can be written with. There are other times there's nothing we can do. E to the x equals 5. There's nothing I can think of to put as make 5 e to some power. No idea. So since the variable is in the exponent, I want to rewrite in logarithmic form. X is the power I put on e, so the natural log, of 5 in order to get 5. This is a great answer. It's a nice exact answer. If you were asked for rounding to decimal places, then you would enter it into your calculator, and on this one I would round to x is approximately 1.609. If the log of x equals 2, I'm tempted, since the x is inside the logarithm, I'm just going to rewrite it. Alright, if there's no base written, it's assumed to be a base of 10. 10 is the power of the log, 10 is the power of the exponential. The log is an exponent, so 2 is the exponent. 2 is the exponent I put on 10 in order to get x. I happen to know that 10 squared is 100. So, seemingly complex problem, easy to solve. If log base 5 of x equals negative 2, I'm still going to rewrite it. Base of 5, base of 5. The log is the exponent, so negative 2 is our exponent. In fact, negative 2 is the power I put on 5 in order to get x. These both say the exact same thing. I know that 5 to the negative 2 is 1 over 5 squared. And 5 squared being 25, it must be that x equals 1/25. If 2 times 5 to the x equals 32, I cannot multiply. I can't multiply this 2 times the 5x because in our order of operations, parentheses, exponents, multiply, divide, add, and subtract. If I have an exponent and there's nothing that can be done, right? I can't do anything with that 5 to the x. There's no way. I'm blocked. I can't go down to the next level. I can't multiply. And if I can multiply, then my best option would be, how about I divide both sides by 2 to get that 2 away from the 5 to the x. So I can't move down, I can't multiply and make this 10 to the x. It's just not possible. I haven't dealt with the exponent yet. So let's divide both sides by 2. And when I divide both sides by 2, I'll end up with 5 to the x equals 16. We'll rewrite that anytime the variable's in the exponent. X is the power to which I raise 5 in order to get 16. And if you have a calculator that has the log base option in the math menu, you could type in log base 5 of 16 and it'll find it for you. And if you don't, remember the change of base formula is log of 16 divided by log of the base, in this case is log of 5, and you get the same answer either way. So if you don't have the fancy button, as long as you have the fancy knowledge, you'll be just fine. Remember, this is the exact answer. This is the approximation. So make sure you know what it is your professor's asking for. If 6 to the x plus 10 equals 47, the first thing I'm going to do is isolate my exponential part. So I'm going to subtract 10 from both sides. Not 11, but 10. And when I subtract 10 from both sides, I'll end up with 6 to the x equals 37. In my head, I'm thinking, hey, x is a little bit bigger than 2. But we'll see. X is the power, right? All x is an exponent. All logarithm is an exponent that I put on 6 in order to get 37. This is a great answer. Nice exact answer. Using a calculator, I can find the decimal approximation to be 2.015. Confirms my suspicion. My answer should be a little bit bigger than 2, and that's truly a little bit. If 4 to the negative 3t equals a tenth, variable in the exponent, I'm going to rewrite. Negative 3t equals log base 4 of a tenth. But I want to get t by itself, so I'm going to divide both sides by negative 3. In my calculator, log base 4 of a tenth, or I'd use the change of base formula to enter this in. Take that answer, divide it by negative 3. Either way, I'm going to get 0.554 as my approximation. Exact answer, log base 4 of a tenth divided by negative 3. And it's over and over the same things. So if I have 8 times 3 to the 6 minus x equals 40, the first thing I'm going to do is divide both sides by 8. When I divide the left by 8, I isolate this exponential part. When I divide the right by 8, 40 divided by 8 is 5. Now that I have the isolated exponential part, I know that 6 minus x is the power that I put on 3 in order to get 5. If I subtract log base 3 of 5 from both sides, add x to both sides, I end up with 6 minus log base 3 of 5 equals x. And of course I can find that decimal using my calculator if I need a decimal approximation. Let's get into something a little more challenging. E to the 2x minus 5 e to the x plus 6 equals 0. Now if I wrote this in the form of, let's use black, y squared, that's a y squared minus 5y plus 6 equals 0. I don't like that looks of that squared, but we'll go with it. You could factor this. You could factor this and solve for y. Well, this really is no different. It's just a more sophisticated version of the same thing. It used to be I'd tell students, substitute, let y equal e to the x, and go from there, but then you have to remember to back substitute. Let's skip that nonsense. You're sophisticated people, you can handle this. E to the x is our variable. It's our variable term as we're factoring, so we'll have e to the x times e to the x gives us e to the 2x. Now I want to multiply two things to give us positive 6. They have the same sign because it's positive, and that sign must be negative, and they add to be 5. So it has to be e to the x minus 3 times e to the x minus 2 equals 0. Equal to 0, I have them factored, so the 0 factor property says e to the x minus 3 equals 0, or e to the x minus 2 equals 0. If e to the x minus 3 equals 0, then e to the x equals 3. A little step I didn't write down. If e to the x equals 3, then x equals the natural log of 3. Similarly, if e to the x minus 2 equals 0, then e to the x equals 2, in which case x equals a natural log of 2, and I can find those decimal approximations on my calculator because you need to. We don't memorize log tables anymore. Back in the day, I'm told they did. I'm not quite that old. It feels like it sometimes, but we use technology these days. Natural log of 2 is approximately 0.693. Let's do another one of those. Now I want two things that multiply to be a negative 36, so I know one's positive and one's negative. They multiply to be 36 and add to be 9. This being positive and these being opposite, right? You have to multiply a positive and a negative to get negative. This tells me that the bigger one is positive. Well, 12 times 3 is 36, and 12 minus 3 is 9. So e to the x plus 12 times e to the x minus 3 equals 0. If e to the x plus 12 equals 0, then e to the x equals negative 12. But we know negative 12 is not in the range of e to the x. The range of the exponential function, the natural exponential function, is only positive numbers. So this will give us an extraneous root. And e to the x equals 3 will give us x equals natural log of 3, which we found in our last example to be 1.099. So watch for these values. They could be extraneous or extra answers as we're going through the process. What about logarithms? Log base 4 of x minus log base 4 of x minus 1 equals a half. Similar to when we had to isolate the exponential part, here we're going to isolate the logarithm, but the logarithm indicates 1. So I'm going to rewrite this left-hand side in a single logarithm, so they're both log base 4. Subtraction of logarithms is the same as dividing the argument of the logs. So log base 4 of x over x minus 1 equals 1/2. I still have my right-hand side. The variables are inside the log, so I want to convert to exponential form. 4 to the 1/2 equals x over x minus 1. Well, 4 to the 1/2, that's the same as 2. Let me rewrite that in for us. 4 to the 1/2 is equal to 2. So if I have 2 equals x times x minus 1, I multiply both sides by my x minus 1. Not exactly sure why I didn't type that in, but that's alright, we can handle it. The x minus 1's cancel on the right, leaving me with an x. On the left, I have 2 times x minus 1. Distribute, 2x minus 2 equals x. I'm going to subtract x, add 2, and I get x equals 2. Check it in the original. You'll find that that works out. And again, remember, if we're adding logarithms of the same base, that turns into multiplication of their arguments. So log base 3 of x plus log base 3. This problem is impossible, but if we typed it correctly, log base 3 of x minus 8 equals 2. We could write that as a single log, as log base 3 of x times x minus 8, or x squared minus 8x, still equals 2. Once we have a single log, I can convert 3 squared equals x squared minus 8x. I know that 3 squared is 9. Anytime I have a quadratic, I'm going to subtract that constant term to the other side, get it equal to 0. Factor and solve. But notice I have here x cannot be negative 1. Why is that? Remember, the domain of a logarithm is only positive numbers. For the same reason, the range of the exponential functions are positive values. Negative 1 minus 8 makes a negative 9. I can't put negative 9 inside a logarithm. It's not in the domain. In fact, I can't even put negative 1 inside the logarithm. So we have to exclude this value. The only legit answer is x equals 9. These are the only possibilities. I check them. X equals 9. 9 minus 8, that's not negative. Actually, not 0. It's like positive. 9 minus 8 is positive. 9, positive. Fantastic. X equals 9 is in the domain. And if I were to check this, we would find that it's the correct answer as well. So this is exponential and logarithmic equations. Kind of boring, kind of a bunch of equations. Solve, 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 solve. But you can do it. We're going to use it in future examples. Thanks for listening.